All right, a couple things real quickly. The top 5 problems on any machine learning project, data consists of number 1, 2, 3, 4, and 5. Not much in second place, okay? So that's why 80% of every project involves data. What we went through yesterday was early days. I'm sure some of you have gotten started already. What you're going to end up doing is taking a look at features, and you're going to pick one feature to predict, et cetera, et cetera. And this is interesting because feature engineering, first thing we list is domain expertise. That's business professionals. That's not data scientists. So first business professionals, followed by analysts. Then you get the term creativity. There's nothing cut and dried about a machine learning project. Now, one of the things we do with a 14-week semester is you have a static project. Okay, there's no such thing in the real world. You're literally, data's coming like a fire hose and you're sampling it and checking it and just continuous. What you're going to do is a static, just snapshot, do the analysis. Where creativity comes into play is what Trucker Brown said, it never ends. So when you get a project going and you get a prediction and you get some metrics, the data keeps flowing in. So it gets to creativity. Also, what you're doing in your projects, even though they're static, is experimental. Every machine learning project is experimental. So what you're going to do is, what I don't want you to do is look at it and go, man, I'm predicting at about 25%. So I'm going to melt down over Thanksgiving and try to get it up to 90%. Don't do that. Look at it and see why it's 25%. And one of the reasons is it's a static project. Okay? Don't worry about it. What you're really looking for is how to explain it. And the fallback, of course, is I may have the wrong features. The data may have changed. I may have, last semester we had a very interesting heart attack data set that we're still playing with the data just for fun, the student and I. And he had a very low heart attack prediction, and we're still trying to figure out data imbalance and that sort of stuff. So don't worry about it. But I'll take a look at your data. You and I can look at it. We can go back and forth, et cetera. My point is, it's experimental. It's always evolving. So you're going to look at data profiles. You're going to look for, naturally, you guys already know what high quality data is. This is all great to have, no question about it. Credibility comes into play with business professionals. So does comprehensiveness, interpretability. I can't tell you, y'all are in the loop totally. You never get out of it. Okay, so you can take a look at data profiling. Now, one of the first things I said, you guys are in the loop a lot. Data lineage, that's coming from the data scientists. You're going to have data engineers over there in that group. That's fine. Where did the data come from? And a lot of companies are now tracking the data as they come in, who changed it, when they changed it, and how they changed it. Some of that's been automated. Your data sources are always interesting. Metadata, of course, is data about data. This, that, and the other, structure, meaning of each field, and so forth. That's not the problem unless a lot of you have features that are highly abbreviated, because I've covered about 2/3 of the data set so far. Whew. First thing I'd do if I were you guys is write out to myself, to yourselves, what each one of those features means. I mean, BX underlying T doesn't mean jack, okay? So you're gonna have to get it in English. So that's just kind of, not surprising, especially those of you with 200 features. Okay, first thing you're gonna look at, and this again is dependent on your data. That's the reason I want you to have a lot of instances. Everybody, you guys know what central tendency is, mean, mean, and mode. Take a look at it. Look at dispersion, look at variance and standard deviation. It's always nice if you have a delightfully normal data set. Every feature is a normal curve. Sometimes you will, sometimes you won't. Like I said, that heart attack database is driving both of us nuts. And I mean, we're at 1 million rows trying to see where the data's gone wrong. And so you said, well, what does that mean? We're trying to predict heart attack. Okay, naturally you think body mass index, are you a smoker? Do you walk more than 10 steps a day? All this kind of stuff. All that's in there. Age, gender. Well, I don't think we've gotten above 8%. And I know that the commercial models, of course, are much higher than that. But so we've got a data problem. But just I want you to look at this. Now, if you get a data problem and we're into October or something like that, then and you send it to me, you and I are going to find a solution within the day. Okay, so don't worry about it. Some of you have very complicated data. You could do any number of things. You do not have to do this on this project. I'm just telling you will in the real world, or your data scientist will. Everybody understands the histogram. You had this in what, 8th grade? That'll give you roughly the distribution. Keep in mind the term bins here. We're going to have to come back to those. Box plot, same thing for quartiles. I tell you what, a lot of this comes up, and you're going to be going iteratively through your notebooks. For example, you get some weird result. Your confusion matrix is off, your accuracy is off or something. Then you're going to go back and look at normal distribution. You'll look at your quartiles and see if you've got imbalanced data. It's always a hoot when you get this. Okay, and then you sit there and you go, well, this is throwing me off, clearly. So that's unbalanced data set. Box plot, same thing to give your quartiles. Now, correlation analysis, you've got a lot of features. Now, every one of you knows, please tell me everybody in here knows multilinearity, okay, where your features are highly correlated. That will mess up your analyses. So you get to figure out what to do about those. We use heat maps. They're beautifully visual, okay? So you end up with, feature 1, feature 2, feature 3, feature 4, and you're looking for all the correlations, all the possibilities, etc. Was it 4 factorial? And so you've got to check those out because it'll throw your analysis off. By the way, that's easily done. Outliers are really interesting. This comes to business professionals. So here's your data set. And you've got scatter plot. I can only show 2 dimensions on the board. Here's your scatter plot. And then you get this. And you're trying to decide, maybe I should go to Mama Goldberg and have a beer before I decide what to do about this outlier. Because, depending on what your data set is, you got 2 choices. One is you ignore those, which is usually the case. The other is one of your business professionals says, wait a minute, that may have really useful information. Healthcare, you don't delete it. Okay, you may not use it in your analysis, but you don't delete it. Okay, same thing with biotech. This is really critical. Drug-drug interactions, drug predictions, that sort of thing. So you could easily check on outliers with your z-scores where you standardized, and z-score is just number of standard deviations out from the mean, plus or minus. Okay, well, that's great. Notice interquartile range here. First quartile on the third, values below 1.5 internet, the interquartile range above and below the mean or potential outliers. You get to decide on that. Chances are, unless you have a real problem with your metrics, don't fool with this, okay? Let me know if that does create a problem. Something like this, by the way, if you've got anything more than 2 features, scatter plot doesn't do you get a 2-dimensional scatter plot, okay? I wouldn't go crazy on that. So if it's erroneous or irrelevant, remove it. You can analyze it independently, like I said. You can use median instead of mean. Everybody know the difference between median and mean? Mean's the average, median is just the central value. This is like when you hear the media is great on this. They go, at age group 60, how much do people have saved for, or what's the net worth of people at age 60 in the United States? Well, on average, $2 million. What's the median? 200,000. Well, obviously, the Jeff Bezoses of the world have dragged it over. So the mean is very sensitive to outliers. The median is not. We're going to come back to that today. And if they represent important events, keep them in your data set. Who decides that? You do. This is not a data scientist gig. They'll do the outliers, and then you're going to look at them. Okay? And decide which one of these four you want to do. Okay. We're over in chapter 5 in the book, by the way. I just came over here because we're doing this now, cleaning up the data. All right, look, you can do three things. Well, two things with missing data. I can delete the stuff that we talked about. If there's too much missing data in the feature, dump it. If there's too much in a row, too much missing data in a row, take the instance out. You can also impute. Now, imputation means replacement. Okay, what do? I've got missing data, and I've got to figure out a way to bring it into the fold, as it were, and so I'm going to replace it. What it does, it'll preserve your sample size because you're not deleting anything. It will cut down on bias. It will maintain your statistical power. This is good, depending on how you impute. All right, here's your concerns. Percentage of missing values and types of missing data. The feature that you're predicting, be very careful on imputation. Okay? 5 to 10% missing data, that's a reasonable amount for imputation. I'm talking in a feature. We're doing feature engineering here. 20 to 30%, okay, you're juggling. If it's 50% or more, very, very risky. I don't know anybody that imputes at 50%. Better to toss the feature. You get to decide 5 to 10, straightforward impute. 20 to 30 means you get to figure it out. Okay. Don't worry about that. Okay, so what we're doing in here, you replace missing values with mean, median, most frequent, which is the mode, or a constant value. Those are your four choices. You don't have to do them all. What you do is, if it's the mean, the program, the notebook will calculate all the values of the feature, come up with the mean, and replace every missing value with the mean. Okay, if you think that your data is skewed, use the mean, go with median. Or mode, either one. Most constant value is fine, median's okay too. Look guys, we're not in here solving the world's problems. Okay, if you pick one, just go ahead. All right, now if you get weird parameters, weird metrics, then you can switch. By the way, it's real quick to switch. Okay? You're not rewriting all this code. I mean, I'll show you about it. This is just a hyperparameter here. This is something that you can change. And a constant value, I don't like constant values because they're hard to choose. And you may be a business professional in a certain area, accounting, finance, HR, and you know more about constant values than I do. So I would pick mean, median, or mode. And then if you do, that's numeric features. Now a lot of you have a lot of numeric features. Well, if you're on categorical features, now pick most frequent or constant. Why? Because I can't do a mean and a mode. I mean a mean and a median. So pick the mode or a constant. That's not bad because a lot of you are going to be predicting categorical features. Again, we're going to do this in the code here in just a minute. All right. Now, all that, everything up to now, 11:14 on Wednesday, is how you replace missing data. Okay? How you replace NaN values. I've got the code in here for white spaces. Some of you are going to run into data sets that don't have NaN in there for missing. It'll just be a white space. So you got to check for white spaces. What will happen is this. you'll take out all the NaN values, okay, just NaN, and you'll run your analysis and it'll kick it out. It'll say cannot process certain values. Well, you got white spaces, so you got to take those out too. So up to now, it's all been about missing data and what to do with it. All right, in coding, I want to transform. Now remember, imputation is replacement. Everybody's straight. You just replace the values. Okay, in coding, I want to transform categorical data into numeric because the machine learning algorithms that we're running will not process male and female, red, green, blue. Not going to happen, okay? It will kick it out on you. The good news is it'll tell you what you did, and like we showed yesterday. Okay, so you got two types, categorical data, nominal and ordinal. Now, this is where the unique values come in on a feature. It's very important when you list all your features, list the unique values in the feature. That way, and their frequency. That way, it will guide your encoding process. Now, you can encode nominally, nominal data, and you can use one-hot or label, one-hot encoding or label encoding. All I want to do is transform categorical to numeric. Okay. Now, let's suppose that you're dealing with a color, red, blue, green. All right, this is your original data. All right, I've got to do something with it. I've got to create a binary column for each category. Now, know what you've got. You're going to do the one-hot encoding Python code, which is already in there. So what do you come out with? I come out with, I've only got 3. Oh, by the way, the feature here is color, and the unique values are red, blue, and green. That's why you always look for red, blue, and the number of unique values in a feature, okay? All right, so what I come up with is what I've got. Red, 1 where it says red, and 0 for blue and green. Blue has 1 when it's on blue, 0's on the others, green. Okay, what you end up with, instead of 1 feature, you have 3. Now, if you have a data set that has, you're looking at types of cars, and you've got 27 models, and you decide to use one-hot encoding. Same code, I'm going to get 27 features instead of 1. It's called the curse of dimensionality. So you get to figure out what you want to do, because what could you do? You could just assign a color to red, blue, and green. Assign red is 1, blue is 2, and green is 3. That's fine except for one thing. What does the program think? It thinks that green is larger than blue, which is larger than red, which means you're implying an order here. Could be more important, or otherwise. So you get to decide. If you're going to run into a ton of new features, you may want to use direct assignment. Okay, now, ordinarily, red, blue, and green don't have an inherent order. Okay, for example, high school, 2-year college, 4-year university, graduate education. Those 4 come up a lot of times in education. Okay, well, obviously they're in an implied order, so it's not unusual. It's usually 1, 2, 3, 4. Postgraduate education of a 4 is more education than high school. You see how that goes. So you just use direct assignment. Okay. Now, don't get confused when you have these new features. Okay. Now, what you don't want to do, what I would do, I would keep the original feature name with an underscore or a, I want to keep the original feature name in there, like car model, Volvo, et cetera, et cetera. So if you do that, you can really keep it straight when you're doing your analysis. We've got that in here. Okay, so this is really up to you. Now, label encoding, I want to just assign them. Okay, so there's red, blue, green, and I encode the data 0, 1, and 2. Generally, if you're going to do direct assignment, start with 0. so you don't confuse the program. And again, it said it may imply an ordinal relationship. So, like I said, the system may look at this and go, least important, in the middle, most important, or greater than. I've not run into, I usually don't use one-hot encoding on gender, because gender is pretty straightforward. Okay, I mean, it doesn't matter 0, 1, 1, 0, depends if you want male, female, female, male. That'll come up a lot. A lot of you have data sets with that in it already. Okay, so this is good because this is, you know, kind of a nice line of code as opposed to going through that. This is probably more rigorous. One-hot encoding probably more rigorous than direct assignment. But we're going to go through all this in a notebook in just a minute. Okay, now ordinal encoding generally maps also because I've got a meaningful order here, small, medium, large, extra large, and so forth, and it's easy to direct assign. Okay. What's interesting is you guys have some really cool data sets, and you get to decide, is there an implicit order in the categorical variables? Okay. All right, now you create features, which we'll do. I put binning here because, first of all, we're going to create some new features along the way here today and next week. But binning, I want to go from numerical data to categorical data. So ordinarily, you go categorical data to numeric data to get the machine learning algorithm to run. But you can also do this from numerical data. What you've got is you have numerical data that you really want to split up. So you have something, say, numerical data like this. Okay, you've got thousands of values here. You don't want to run a regression, or you've already run the regression. So all you do, you get to figure out, are you going to go to deciles, quartiles, which are the only things we talk about this semester. You can pick anything you want. But obviously, if I've got a bunch of features here, I want to go to deciles, I'd put them in groups. If I've got 1,000 of these things, every one of these deciles has 100 values in it. Okay, then you just assign the number. Now, in this particular case, it is definitively in order. Okay, so your first decile is 1, your second one's 2, third one's 3, etc. Okay, now, what do I have? I now have categorical data. You get to decide on this. If you want to use quartiles, I just split it up into 4. Easy to check. They're equal size bins. If you have skewed data, don't do this. Okay. It'll be, or you can truncate the data, like I said, where this curve goes off, like this. You better truncate the data right there, then go ahead and bin it. This is something that you may use, you may not. I just put it up there because every now and then it really is nice on analysis. We do combine features that we will talk about. We have the code for that. Fortunately, we're not worried about text in here. Some of you had product descriptions that are this long, and I said what I would do is get another data set. Okay, why? Because we're not doing natural language processing in here. Time-based features, same thing. And then you get to normalization standardization. I tell you, I'd probably give this some thought, especially for your neural network. You're all going to be running what would I call a simple neural network, feed forward back propagation, so you're going to need to be normalized. Okay, and so you get the data here, fix the data this fixed range, usually 0 and 1, and standardization. It's slightly different, but what do you get your numbers back in? You get them positive and negative based on how far they are off the mean and a z-score. Okay, that, trust me, it will. Your neural network is not going to converge real well if you have orders of magnitude different in your features. Say one feature is a house price and it's hundreds of thousands of dollars. And then another feature is number of bedrooms, 2, 3, or 4. Okay, the neural network's going to just be grinding on that. Okay, but if you standardize on the house value. Okay, the mean's 300,000, you get the picture, and number of bedrooms is average is 2.7, you see. Okay, now everything's on the same scale. So it really does help. Okay. I know you're getting this like a fire hose, but it'll show up in the notebooks. All right, this is what we were playing with yesterday. Oh, by the way, has anybody looked through the appendix yet? Okay, when you get the book, you go through vital source. Appendix is the last, and it walks you through every bit of this code. So these are code libraries. NumPy does numerics, Pandas does organization, missing numbers. XLRD is imported when you use the new XLSX data sets. Seaborn gives you some visualization and so forth. Any code library that you want to put in there, you'll see in these examples. And by the way, it's okay if you decide in your notebook that you want to import 25 code libraries right to first. You may not use them all, but they're there. Okay, you're kind of like your call. Then you mount Google Drive. That's the code. Then we went through this. Don't do what I did. In other words, I have ML data for my data. When your data set just comes right in here at the end of this content drive, my drive. Content drive and my drive are established for you as soon as you get through Colab and go to your first notebook. Okay. Then we did all this. We looked at the different suffixes to the data sets. And this shows you how to load them up. I've commented everything out. By the way, you can comment out anything. Suppose you've got code that you want to look at, just put the hashtag out beside executable code. It'll turn green, it won't execute. So we looked at shape, size. This is DF head with no number in there, so it's first 5 rows, starts with a 0, 0 through 4. It's really cool the first time you do this because you guys will get a chance to look at all of these across the top. If you have more than fits the page, you'll see the ellipse that we talked about, etc. This way to list it is like this vertically. Then you can come down and I get the number of unique values in each feature. I'm very happy. And there are all different ways to list it here. By the way, you don't have to do all these on your notebooks. Just pick one. What I'd do is I'd list it right here. Okay, now, number of unique values, very important. High numbers, numeric. Low numbers, categorical in general. Then this is a subset of categorical features. You got those that you could look at from here. And what's interesting is, even though I have 31 values here, that's a contributing factor for vehicle 2 in the accident, still categorical. So I come down. Then I've got the unique values and another way to list them so I can see them all. This particular code lists it sideways, linearly, so you can take a look at it a little bit easier. Missing values, very important. We talked about you can look at it this way or you can list them and take a look at it this way. And percentage of null values, that's great. By the way, if you get high numbers like this, you know what to do. This is the type of value. Object means categorical. Float means numeric. Okay, went through that. This happened to be, I had to drop a bunch of these because these were all a lot of missing data, and we didn't need latitude, longitude, and location, so we dropped them. As soon as you do that, I print the features, and here they are. What have I done? That's 11 I think we took out. Okay, I just showed you how you cram some together if you'd like. You may have that in your data sets. This is called combining features. Okay, keep in mind, every time that you drop features, rename your data set. Okay, in this particular case, let's see where we started. DF modified. Data frames, what we started with. Yeah, categorical features here. We're still in the data frame, which is our original data frame. Remember, keep your original data set. There it is, print data frame unique, okay? Then we came down, dropped all those features, went to modified, so DF modified. Now, I can tell you now, I have torn my hair out more than once because down in the code, I will back check with DF head just to see what it looks like, you know, the first 5 rows. But I've gone to modified and I forgot it. And I can assure you, Linda heard me yelling all the way downstairs. So when you do that, check your data frame name, okay? Now, so we're playing with diff modified. Then you can list your DF head this way only. Make sure it's DF modified head, not DF head, or you'll get the original. Okay, so I look for missing values, percentages. I want to get rid of some more stuff. We talked about threshold of 50% for dropping instances. We didn't have any, so we still have 7,300 rows, but only 12 columns. It was 26. Okay, so I look for null values. What I'm really looking for here is all zeros. All right, so I get some NaN values. I get the more out of there. Now I get down here. I'm very excited. So now I'm down to DF clean. Now, when you look at this, when you go to encoding, what do I have? I have all these unique values. So what in this particular case, I'm going to use a factor map and a vehicle map. Because what do I have? I'm looking at DF, DF modified, but what I want to do, DF clean, I'm sorry. What I want to do is keep a copy of DF clean, so I just let DF encoded equal DF clean. And I put copy here, so now I have the DF copy, the clean copy, and I'm playing with encoding. So DF clean, you'll still have it, but now I'm going to encode what I need to. I cannot use failure to yield right away and lost consciousness. What I have to do is assign those. Now, encode those. It is possible, if you wanted to use one-hot encoding here, if you really wanted to. Or, in this particular case, it's just direct assignment. So the factor means factor contributing to the collision, and the vehicle is the type of vehicle in the accident. So I call them factor map, vehicle map. Notice it's direct assignment. Okay, now I've got to apply the mappings to the relevant features or columns. That's this code. So I come down and I see, oh, this is great. I'm looking for, make sure the encoding's in there. And so notice contributing factor 1, zeros and ones. I've got NaN right here, so I've missed something. And so I don't worry about this. This is one of those features that we just shoved in there that we combined, by the way, Burrow zip on street. So I'm reasonably happy, but now I need to print the null values. Well, it looks like contributing factor vehicle 2, I have 2,900 of these, which is 40%, so I toss it. So I get rid of vehicle 2, I'm looking for DF encoded head, and I see everything is nicely done with encoding. Notice, I left this in here because it's not necessary that you use every feature in your analyses. Okay, if I'd thought about this, I'd have dumped it. Okay, I'd have gotten rid of this right-hand value, this right-hand feature. Now, when you get through with this, you've got a clean data set. Now, here's the key. You don't have to do this again. What I want you to do, I've got this DF encoded, which is my most recent clean data set. Remember, we had clean, now we're encoded. We're really happy. Put a -3 behind it and save it, and it'll show up in your data. That's the data set you'll be using going forward. Everybody see this? Your other, when you get to your other cell blocks, you start doing regression and logistic regression and decision trees and so forth, that's the data set you'll use. It's already clean. You just go straight to it. Okay, that's the data set you'll import. Now, do you have to go back up to the top? No. What I want you to do is you've got it right here. Let's suppose we started, let's see here. All right, so here I want to do a logistic regression. I've already saved this as the DF encoded, it'll come in DF encoded -3. All right, it'll be a CSV file, comma separated values. And all I do is, I've already got it, I use it for my analyses. And your analyses, your algorithm just run one after the other. You do not go back and redo all the stuff up at the top. You're only going to do that once. Make sure your data set's clean though. You get down there to here and you get ready to start using it. Okay, on this particular notebook, I said, let's go ahead. I've had a bunch of discussions with you guys about reducing. All right, here's what you do. Now, by the way, we're done here. In other words, with what we're doing in this data profile, you've got the clean data set. You can stop there. I mean, you can use that when you start doing your algorithms. I just stuck randomly reducing in here at the bottom because I want to do it early. Notice, sample size is equal to the length back to DF. I did the original data set because that's what we're going to randomly reduce. It has to be random. Okay? I've had Excel wizards before on a 500,000 row data set decide they're just going to take the first 50,000 rows. And evidently they knew how to do that in Excel. So they did that off to the side and brought it in. Why won't that work?
Well, because one set of the data could be skewed or not accurately depict the rest of the data. So you want a random set so you get a more accurate picture of the entire set.
Absolutely. You have no idea the variety of data in a couple 100,000 rows. Okay, imagine you're in the real world. By the way, the real world, you don't reduce unless you got a special project going on. But in this particular case, I'm back to the original data set just for purposes of illustration here. From this point right here on down, it's just, I'm looking at randomly reducing. Doesn't have anything to do with how we clean the data. I divide by 2. Okay, I split the data set down. If you guys have 500,000 rows, you want to do 100,000 rows, you put a 5 in there. Okay, you've got control. Anytime you see a green, now I'm not talking about a comment, some green value in your code, that's a hyperparameter that you can adjust. Okay, so you could do any number here you wanted to. I wouldn't overdo it, but if it's grinding your computer at home or something, then you can go to 3 or 4, whatever you want to do. All right, so that's setting your sample size. Random sample, that's DF sample size, and don't worry about the random state 42. This is for reproducibility, but just always use random state 42 in here. Okay, we're not going to be data scientists. Well, you may be, but I'm not. Okay. All right. So there's a shape. I want to look at it. So what I've done, I cut that original data set in half, instances. What did it do? It kept exactly half the instances. I still have 26 features. Okay, that's what you want. This does not affect features, it affects instances. Now, every single time, I want you to go back in there when you do this, and if you go ahead, you could split it into a third or a fourth. Be careful though, you want to preserve instances if you can. What I want to do, I want to see, I'm happy with the columns. I know I've got 26 still. I'm back checking to make sure they're all here. Notice everything's original. So I come down here. Now I want to look at the number of unique features, the number of unique values in each feature. Okay? Now, make sure you do this. The reason that if you take this value right here, 207 dates, 700 times, so forth, what you really want is something that pretty closely approximates. It's missing, we've done unique values. I want you to be very close, that you get as close to the unique values ratio-wise that you have up here. Okay, this is your original data set. So check this against the one down here at the bottom to make sure there's nothing that's been left out that is truly random. If it is, these will at least approximate what you have. Okay? And a lot of you will be doing reduction. Okay? Okay, we ran a quick made-up data set here a couple semesters ago. It's just we made up the name category samples, 400 instances, 4 values. Here's the first 5 rows. What we did, we put colors, cars, shirts, and weight, and we have 400 rows and 4 instances. These have nothing to do with each other. We just stuck them in there to illustrate data profiling. So you get the data features, colors, cars, shirts, weight, and you've got them right here. Now look for unique values the same way. Medium, small, large, extra small, all these colors and values for cars. Okay, in other words, I've got all these models of cars, here are the colors, shirts, weight. Now, ordinal data encoding. Got to change the values of the shirts featured numeric values. Do not look at this. Look at this up here. How do you do it? What would you do just knowing I had to encode shirts? You got two choices. What do you do?
I do the numeric values. Like, since all the shirt sizes go in a numeric order, you could put them in the...
Okay, I have an implied order. I can do 0, 1, 2, 3, and 4, right? Okay. All right. The other choice is, and there are sometimes people want one hot encode. I would not just assign the numbers. Okay, because it has an implied order. Now, unique values and colors, blue, red, white, green, yellow, we've already done that. As you all know, 2 ways. Direct assignment, which implies that perhaps blue is greater than red is greater than white, or one hot encoded. Now, that's pretty simple on color, but if you look at the cars, and you're running this analysis, and you're kind of thinking to yourself, well, Buick, Toyota, Chevrolet, Nissan, Ford, Cadillac, and Land Rover are the most expensive, etc. You could say, well, maybe I'll try to organize them by expense or stuff like that. I wouldn't do that because you don't know which type of Cadillac or Land Rover you got. Okay? So, one hot encode them. If you don't, you're going to have Cadillac and Land Rover, which are indeed more expensive or more luxurious than the rest of them. But the best thing to do here is you one hot encode those. Now, this is another way to do this. I'm looking at the data frame for shirts, and notice I put them in order because you've got this up here. Now, by the way, it's case sensitive. Got the vertical apostrophes, and what am I doing? I'm assigning 0, 1, 2, 3, and 4 right here. Now, check DF head. The reason I do that is to take a look and see what I'm looking at under shirts. So instead of shirts looking this way, small, medium, large, I now have shirts with numeric values, and now I want to get down to what in the world I do with colors and cars. Okay, we just said one hot encoding. I can do that with multiple columns. I got to specify the columns. Then I go in here and I encode those. Now here's what you're going to run into. Sometimes you'll one hot encode and you'll get true false. Okay, do not worry. You just have to put another line of code in to move the true false to 0 and 1. Okay, trust me, if you try to run your analysis with true and false, it's going to kick you out. Okay, so what do? You've got that line of code right there, integer. Okay, so now I've got all the integers. What have I done? I've gone to, well, let's see, a whole bunch of columns. I've got the curse of dimensionality with brand new features in there because I've got all these colors and all these cars. Okay, I've still got weight. Weight's kind of interesting because it's numeric, it's continuous. So I've handled shirts, I've handled colors and cars. Now, come on down. I want to look at the shape and size. So instead of 400, I've got 1600 because I have 16 features instead of the original 4. All right, now, I'm looking at weight because it's numeric. Some of you may want to do this because you've got some real interesting data sets. And so you've got the usual, there's the count, the mean, standard deviation, minimum, there are your quartiles and so forth. Your box plot, let's get this down here. Okay, there's a distribution of weight. And now, if you decide that you're looking at weight and you want to bin it, what I want to do, I've only got 18 unique values in weight. So deciles would be very difficult, so I can do quartiles. Here's the code for quartiles. These are the labels. Q1, 2, 3, and 4. And I want to see the quartile distribution. 29, 25, 24, 22. Well, that's interesting because they didn't give it to me in order. So 29 here, 22, 25, 24. I'm pretty happy. Okay? Nothing's bizarre. If you do get something bizarre, what do you have? You have an unbalanced data set, a skewed data set, or a skewed feature, excuse me. Okay? So this gives you the quartile midpoints, 121 pounds, 166, 182, 201. Then you can create the mapping dictionary here. It's another way to do direct assignment, which I did. You can't use Q1, Q2. So I just assigned it 1, 2, 3, and 4. And there you have it. Shirts, weight, and then I kept weight in there so you can see this. The weight of 167 is Q3, and weight quartiles number is 3. When you do your analysis, this will be the feature you use. Okay? You can use this feature, but if you'll notice, your order of magnitude is off. It's much easier to do that. Okay? It'll be a lot cleaner analysis. Y'all getting all this through a fire hose? Too bad. Here comes a note. All right. Moving up a notch. This is California housing. It does an analysis of the price of housing, et cetera, et cetera. Now, we've got all this stuff we're going to use here. These are all code libraries. And we're going to come back about scaling and imputing. After drive, do the same thing. What I'm pulling in this particular case is California housing. Okay, so I come down. I want to check the size of it. 20,000 rows, 20,000 inches, 10 features. So let's take a look at it. Okay, latitude, longitude, which is clearly some type of location. Median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. This is a live data set. I mean, this is pulled out of a live data set. They look squirrely up there before we even start. Anything look strange to you that you would really want to look at?
To be honest, it's a little hard to read. To be honest, it's a little small to read.
A little small to see?
A little bit, yeah.
Oh, okay.
I need to come set up close.
I'm standing up real close to it. If I couldn't see it. Okay. Latitude, longitude, age of the house, total rooms, total bedrooms. Now, the population here is in a census block. Okay, so 322,000 people in that census block and so forth. This is the number of households in that census block. Actually, this is probably 32,000. Median income is the median income of, tens of thousands of the household itself. That's your median house value in dollars, and ocean proximity has 4 or 5 different unique values. So those of you who can see, does anything look a little swirly up here?
Looks like some of the latitude and longitude repeated.
Where is it repeated?
Rows 3 and 4 have the same latitude and longitude.
Yeah, because they're in the same census block. You're exactly right. Different houses, same census block. Okay, but here's the interesting thing. There's quite a bit of code you could write to put latitude and longitude to a specific address. Okay, my question is, oh, by the way, first thing off the top of your head, what would you be predicting here? Just for your data set, what would you be predicting for your class project?
If you were to sell a house, what would it be worth?
Yeah. What's the value? Okay, so you're looking at your dependent variable right there. That's your predictor. You're predicting, what you're going to be predicting. Latitude, longitude, well, I've got ocean proximity over here. I've got census blocks all over the place. I'm probably going to toss those two. Okay. What about total bedrooms and total rooms?
I guess the ratio to bedrooms to rooms, higher bedroom to room ratio means smaller houses.
Yeah, and you got several choices here, but number one, the first thing you're thinking to yourself is they're highly correlated. You may want to toss one. Some people, you guys are buying a house. Would you look at total rooms or total bedrooms first?
Bedrooms.
Everybody does that. Then followed by what? Baths. So if you look at this, you can see there's a very limited amount of data here to predict that price. Okay, but it's great for our purposes because first couple things, you probably got location covered somehow roughly with ocean proximity. You probably dump these two. I personally didn't want to write the Python code to find an address. Okay, besides, houses change, in a neighborhood. All right, so when you start looking at stuff like this, I'm going to take a hard look right here. I've identified the dependent variable. I'm tossing these two and we'll proceed. Okay. Now, last time I looked, I heard Monday was a national holiday. Is that true? That means we're going to slack off for a week. All right. Well, then next Wednesday, okay. Outreach students, next Wednesday. Is anybody going out of the country?
Oh, I wish.
Oh, good, because I'd have to fail you. All right, I'll see you all then. We'll press on. Do not come back in here with tan better than mine.